In the previous video, I covered the essentials of screening data before starting the statistical analysis and included the download link for exercise 2 in the video description. You can refer to the previous video to gain insights into data cleaning techniques. In this video, I will overview the assumption of normality in parametric statistical tests and the application of transformations to address non-normality. Please subscribe and click the bell icon to receive notifications when new videos are released. A seminal Monte Carlo simulation study recently published by Neef and Forstmeyer, 2021, has demonstrated that contrary to what was previously thought, violating the assumption of normality does not cause sharp increase in type I error or substantial decrease in statistical power, because parametric tests, despite assuming normality, are robust to non-normal data over a wide range of conditions, meaning that they produce p-values that remain relatively reliable except for the presence of influential outliers in the dataset. Another simulation study on using t-student tests with extremely small sample sizes also has indicated that despite the assumption violations such as non-normality, inequality of variances, and inequality of participants in groups and other issues like small sample sizes, parametric t-test demonstrates superior performance compared to non-parametric alternatives both in terms of false positive rates and statistical power. See De Winter, 2013 for more details. Consequently, when assumptions are violated, immediate recourse to non-parametric tests is not recommended. In the case of continuous data, researchers are cautioned against using non-parametric alternatives to t-test and ANOVA due to their excessive concern regarding non-normality. Instead, as suggested by Neef and Forstmeyer, 2021, preparing data using transformations is often advisable, and visual inspection for outliers and heteroscedasticity is important prior to analysis. Therefore, non-parametric statistical tests should only be considered and the variables under study are ordinal or nominal in nature. Please stay with us until the end of the video, as we'll be introducing data transformation methods used to normalize positively skewed or right-skewed distributions, including square root and logarithmic transformations. We will also examine other transformation methods that are used to normalize negatively skewed or left-skewed distributions, quadratic and cubic transformations. Suppose in a study, we aim to explore the relationship between the two continuous variables, age and sleep quality of the participants. We open the SPSS data file for this study. A good idea before starting statistical analysis is to examine the distributions of each variable using the Explore command in SPSS. Click the Explore command from the following path. Analyze, Descriptive Statistics, Explore. In the Explore dialog box, input sleep quality and age variables into the dependent box and the case ID into the Label Cases by box. From the Statistics menu, check the Outlier Data checkbox and click Continue. Also, from the Plots menu, tick the Histogram and Normality Plots with Tests checkboxes and click Continue and OK. A quick overview of the output file shows that the skewness for the sleep quality variable is a positive value greater than 1, which means that the distribution of the sleep quality variable is positively skewed or skewed to the right. In the histogram chart, the skew to the right is clearly visible. Usually, if the absolute value of both skewness and kurtosis is smaller than 1, the deviation from normality is not a problem and it can be simply ignored. The skewness for the age variable is a negative value, which means that the distribution of the age in the present study is negatively skewed or skewed to the left. Again in the histogram chart, the skew to the left is clearly visible. Now I show how the implementation of each of the transformations affects the distribution of sleep quality and age variables in this study. This is the histogram of the sleep quality variable in the present study. As can be seen, this is a right-skewed or positively skewed distribution. And this one is the histogram chart of the age variable. As can be seen, this is a left-skewed or negatively skewed distribution. Applying a square root transformation to a variable compresses higher values while spreading out lower values. Logarithmic transformation accomplishes the same but more aggressively. See the web page by Churi, 2024, titled Square Root Transformation, a Beginner's Guide. Please pay attention to the arrangement of points. It is expected that this functioning will normalize variables with positively skewed or right-skewed distributions like the sleep quality in the present study, and on the other hand, it will worsen the non-normality in negatively skewed or left-skewed variables like the age variable in the current study. This slide shows the effect of square root and logarithmic transformations on the sleep quality variable. The histogram in the upper left displays the original sleep quality variable. Below is the representation after applying square root transformation, while the upper right exhibits the result of logarithmic transformation. It seems that logarithmic transformation has performed better in this case. When positive skewness is severe, it is recommended to use a logarithmic transformation. This one shows the effect of square root and logarithmic transformations on the age variable in the present study. Undoubtedly, not only these transformations does not normalize the distribution, but also increase the intensity of the negative skewness in age distribution, and that the negative skewness is more severe in logarithmic transformation in upper right corner. On the contrary, quadratic and cubic transformations produce effects opposite to square root and logarithmic transformations. Therefore, they are employed to normalize variables exhibiting negative or left skewness. In fact, quadratic and cubic transformations stretch the distances between large values in a set and move them away from each other, and on the other hand, they compress small values and make them closer together. Please pay attention to the arrangement of points. Now we examine the effect of quadratic and cubic transformations on age and sleep quality variables in the present study. This slide illustrates the impact of quadratic and cubic transformations on the age variable. It's evident that the quadratic transformation has effectively normalized the age variable. However, the cubic transformation's extreme effect has resulted in a slight positive skewness in the age variable. Therefore, it is recommended to use quadratic transformation in cases where the severity of the negative skewness is moderate. This one illustrates the impact of quadratic and cubic transformations on the sleep quality variable. We can see that the quadratic transformation not only did not reduce the positive skewness in the distribution of sleep quality, but made it worse. Logarithmic transformation has also worsened the positive skewness in the distribution of sleep quality. Now, let's proceed to demonstrate how these transformations are executed in SPSS. To perform the square root transformation, ensure that the variable is continuous and have non-negative values, since square root of a negative number is not defined. Compute the square root transformation. Click on Transform from the menu bar. Choose Compute Variable from the drop-down menu. Define the transformation. In the Target Variable field, enter a name for the new variable that will store the square root transformed values. In the Numeric Expression field, enter the formula for the square root transformation. Type the abbreviated letters SQRT followed by parentheses. Within the parentheses, insert the age variable by double-clicking it from the left-hand box. Click OK to perform the computation. After computing the new variable, you will see it added to your dataset in the Data View window. To perform logarithmic transformation, ensure that the variable is continuous and have positive values since the logarithm of 0 or a negative number is undefined. Compute the logarithmic transformation. Click on Transform from the menu bar. Choose Compute Variable from the drop-down menu. Define the transformation. In the Target Variable field, enter a name for the new variable that will store the logarithmically transformed values. In the Numeric Expression field, enter the formula for the logarithmic transformation. Type the abbreviated letters and numbers LG10 followed by parentheses. Within the parentheses, insert the age variable by double-clicking it from the left-hand box. Click OK to perform the computation. After computing the new variable, you will see it added to your dataset in the Data View window. To perform quadratic or cubic transformation, ensure that the variable is continuous. In the case of quadratic transformation, it is also better to ensure that all variable values have the same sign. For example, they are all positive or all negative. Otherwise, it may be difficult or impossible to interpret the results after quadratic transformation. Compute the quadratic or cubic transformation. Click on Transform from the menu bar. Choose Compute Variable from the drop-down menu. Define the transformation. In the Target Variable field, enter a name for the new variable that will store the quadratic or cubic transformed values. In the Numeric Expression field, enter the formula for the quadratic or cubic transformation. For example, type age** or age**2 for quadratic transformation. For cubic transformation you can type age** or age**3 in the numeric expression field. Click OK to perform the computation. After computing the new variable, you will see it added to your dataset in the Data View window. Exercise 3. I have put the download link of the SPSS data file that I used in this video below in the description. Please download this file and practice all the skills I taught in this video to enhance your learning experience. In the upcoming videos, I will offer tutorials on the utilization of non-parametric statistical tests for ordinal and nominal data. Please note that the spoken presentation in this video is generated using AI text-to-speech technology to enhance communication clarity and mitigate potential pronunciation ambiguities. I hope this video has been valuable to you. Stay tuned for forthcoming videos.